travel across Europe and the rails, hum beneath a web of overhead wires, but cross America and those wires almost vanish. Why does the world's richest, most industrialized nation run its trains on diesel? Overhead electrification is a highly mature, efficient technology operating at a massive scale. It is not an experimental concept. By 2024, the European Union's electrified rail network reached an average of 57.6%, with several nations running 90% of their trains under wires. Yet across the Atlantic, the United States presents a completely different reality. Less than 1% of the American mainline rail network is electrified. Out of roughly 140,000 miles of track, fewer than 1,200 route miles run under overhead catenary wires, almost entirely concentrated on Amtrak's Northeast Corridor between Washington, D.C. and Boston. Calling one system advanced and the other backward fails to explain this sharp divergence. The physical laws of electricity do not change at the shoreline, nor do the clear engineering benefits of electric traction. Electric trains offer faster acceleration, lower maintenance costs, and zero direct emissions. These advantages are not theoretical. They have been demonstrated on thousands of miles of track for over a century, proving their reliability in the freezing Scandinavian winters and across the high-speed corridors of France and Spain. Because the technology is undeniably superior on paper, the explanation for this massive divide lies deeper than engineering. To understand why these two industrial giants chose such opposite paths, we have to look beyond the locomotives themselves. Infrastructure is never built in a vacuum. It is shaped by a distinct set of economic incentives, geographic realities, and institutional structures. The real puzzle lies in how the underlying business models of moving traffic overland forced Europe to wire its continent, while driving America to rely on diesel. Europe and the United States did not build the same kind of railroad. They designed their networks to solve entirely different problems, resulting in two distinct systems that happen to run on steel tracks, but share almost nothing else in common. One system was built to move people. Across Europe, railways evolved to connect historic cities situated relatively close to one another. The primary goal is speed, frequency, and reliable passenger travel through high-density corridors. In this environment, where millions of commuters depend on precise timetables every day, the high acceleration and rapid turnaround of electric trains make perfect sense. The other system was built to move goods. In North America, railroads evolved to haul massive volumes of freight, coal, grain, and double-stack shipping containers across a vast continental expanse. Here, the primary goals are keeping operating costs low and maintaining maximum flexibility over thousands of miles of single-track lines. To move a single train that is 2 miles long and weighs 20,000 tons, brute pulling power and long-range reliability matter far more than rapid acceleration or high speeds. This fundamental split between passenger-heavy and freight-heavy networks is the organizing principle behind every single infrastructure choice on both continents. It explains why a wire overhead makes perfect economic sense in Belgium or France, while remaining an expensive liability in Wyoming or Nebraska. Every difference in funding, technology, and daily operations that follows stems from this single, basic division. One network is a high-speed transit system for people, while the other is a heavy-duty conveyor belt for industrial wealth. American railroads operate on a scale that is difficult to overstate. This vast network is dominated by a handful of massive, privately owned Class I freight operators, including Union Pacific, BNSF, CSX, and Norfolk Southern. These corporations do not exist to transport commuters or maintain frequent passenger timetables. Instead, they operate as a heavy-duty continental conveyor belt designed to move immense quantities of bulk goods over thousands of miles. The lifeblood of this business model is the heavy unit train, carrying coal, grain, agricultural products, and miles of double-stacked shipping containers from coast to coast. For these private operators, the ultimate goal is moving the maximum amount of tonnage at the lowest possible cost. A single American freight train can stretch over 2 miles in length, weigh more than 20,000 tons, and require several locomotives linked together to distribute the pulling power. In this heavy haul environment, transit time is measured in days rather than minutes. The key operational metrics are not high speeds or passenger comfort, but reliability, route capacity, and maximum flexibility. To achieve this, the entire American rail network is designed around the self-powered locomotive. A diesel-electric engine carries its own fuel and power plant on board. This allows it to go anywhere the steel rails lead, completely independent of any external power infrastructure. If a storm knocks down trees in a remote mountain pass, or a derailment blocks a main line, a dispatcher can easily reroute a diesel-powered train over hundreds of miles of alternative tracks. There is no need to worry about whether those detour lines have expensive overhead electrical wires installed. For private companies that must build and maintain their own tracks with their own money, the flexibility of diesel is a major economic advantage. Installing and maintaining overhead catenary wires across a sprawling 140,000-mile network is an incredibly capital-intensive endeavor. On routes where only a few trains run each day, the investment simply does not generate enough return. By relying on highly efficient, self-contained diesel locomotives, American railroads created a system that maximizes cargo capacity and operating reach while avoiding the massive fixed overhead of electrification. It is a business model built entirely on the logic of massive volume and long-distance flexibility. Wiring a short railway corridor requires significant capital, but wiring an entire continent is a fundamentally different challenge. The physical geography of Europe inherently supports electrification because population centers are clustered close together. A typical European rail corridor connects major cities separated by only a few dozen miles, allowing infrastructure managers to concentrate investment where traffic is constantly high. In this dense environment, a single mile of overhead wire might serve dozens of trains every single day, allowing the high initial installation costs to be amortized rapidly across millions of passenger kilometers. When this same engineering formula is applied to the United States, the geography breaks the economic model. The American rail network spans a vast continental landmass, where route miles stretch across immense distances through sparsely populated regions. On a single track line running through the plains of Nebraska or the deserts of New Mexico, only a handful of freight trains might pass by each day. When trains are spread this far apart, the traffic density per segment of track drops precipitously. The cost of installing and maintaining overhead catenary wires, which can exceed $5 million per mile, is the same whether 50 trains use them daily or only 5. This economic reality explains why the rare exceptions of electrification in the United States occur precisely where European-style density exists. The Amtrak-owned Northeast Corridor, running 457 miles between Washington, D.C. and Boston, functions on this exact principle. It is the most heavily traveled passenger route in North America, carrying millions of commuters through a tightly packed megalopolis. Here, and in a few urban commuter networks, passenger density justifies the massive fixed overhead of catenary systems. Outside these dense metropolitan islands, geography acts as a structural barrier to electrification. The financial calculation of hanging overhead wires depends entirely on who signs the checks. In Europe, the entities that own and maintain the tracks are state-backed, publicly funded infrastructure managers. In France, the national rail network is owned by SNCF Réseau, a public company backed by the French government. In Germany, the federal rail network is managed by DB Infrago AG, a public interest company owned by the federal government. Switzerland's highly electrified tracks belong to SBB Infrastructure, a division of the state-owned Federal Railways. For these public entities, the massive capital required for electrification is treated as a long-term public investment, funded through national budgets and European Union grants to achieve broad policy goals like energy security and environmental protection. In the United States, the entire system operates under a completely different economic reality. The vast mainline network is not public property. Instead, private Class 1 corporations, such as Union Pacific, BNSF, CSX, and Norfolk Southern, own and maintain their tracks. These companies do not receive regular government subsidies to build or maintain their corridors. Every mile of track, every signal, and every bridge must be paid for out of their own corporate revenues. This ownership split traces back to the aftermath of the Second World War. While war-torn European nations nationalized their shattered networks and used public reconstruction funds to rebuild and electrify, American railroads remained private, consolidating their networks and focusing on freight efficiency. For a private American railroad, spending $5 to $7 million per mile to install overhead catenary wires represents an astronomical capital expenditure that must generate a direct, near-term return for shareholders. Because these railroads operate heavy freight trains over vast distances with lower traffic density than European passenger corridors, the investment cannot be justified on a corporate balance sheet. A private business must protect its near-term returns, making flexible diesel locomotives the only logical choice, while public systems can prioritize the long-horizon benefits of electric wires. A diesel-electric locomotive functions as a mobile power plant. Under the hood, a large diesel engine, known as the prime mover, burns fuel to turn a crankshaft. This spinning shaft does not drive the axles directly. Instead, it turns a giant generator or alternator, converting mechanical energy into electricity. This electrical current is then sent through heavy cables down to traction motors mounted directly on each axle, which spin the wheels. In essence, a diesel-electric locomotive is an electric train that carries its own power station on board. No overhead catenary wires are needed. For freight operators moving heavy loads across a vast continent, this self-contained design was a massive advantage. The mechanics of the machine itself explain why America chose a different path. The historical turning point arrived in November 1939 with the introduction of the Electromotive Division's FT demonstrator. The EMD-FT was a 1,350 horsepower locomotive powered by a 16-cylinder, two-stroke Model 567 engine. By pairing cab units and boosters, the locomotive generated a starting tractive effort of 55,000 pounds. To convince skeptical railroad executives, EMD sent the FT on an extensive nationwide tour across dozens of private railroads. The results were undeniable. During trials, the FT hauled 3,000-ton freight trains over steep mountain grades that typically required multiple steam engines, and it did so at half the operating cost. While coal cost about $2.36 per ton, diesel fuel was only 4.4 cents per gallon. By 1945, the fleet of FT-type units across all Class 1 railroads exceeded 1,000 engines. Instead of investing billions in overhead wires, American railroads bought self-powered locomotives, cementing a diesel-electric system that remains the standard to this day. In mature markets, a standard double-track mainline electrification project runs between $5 million and $7 million per track kilometer. When projects face complex terrain, the price can climb even higher, reaching up to $9 million per kilometer. This price tag covers far more than the copper wire hanging overhead. It includes the entire power delivery system. Heavy-duty traction substations must be constructed at regular intervals to feed power from the commercial grid. Signaling and communication systems require extensive modification to block electrical interference, and low overhead clearances under historic bridges and through deep tunnels must be physically carved out. Because this initial capital outlay is massive, the decision to electrify hinges entirely on payback logic. For the investment to succeed, a railroad must have enough traffic to spread these fixed costs over millions of operations. A high-volume corridor requires a traffic density of at least 10 million ton kilometers per kilometer per year. Under these conditions, and assuming electricity prices remain below 20 cents per kilowatt hour, the operational savings can slowly amortize the upfront cost over a standard 30-year depreciation cycle. Dense corridors can spread these immense costs across dozens of trains every single day. But on the sprawling, single-track freight routes of the American West, where only a few massive trains pass each day, the traffic density per kilometer of track drops far below the break-even line. Hanging millions of dollars of wire over a route that sees only 6 trains a day is a financial impossibility. On these sparse corridors, the interest on the initial debt outpaces any potential fuel savings. This is where the diesel option starts looking like the only rational choice. The massive capital costs of catenary infrastructure did not stop Europe's railways from expanding their wired networks. Instead, a series of geopolitical and economic shocks turned an engineering option into a permanent national mandate. In October 1973, the OPEC oil embargo sent petroleum prices soaring, exposing the extreme vulnerability of European transport networks that relied on imported oil. France, which consumed 90 million tons of oil-derived carbon annually, immediately saw diesel traction as a strategic risk. The French government directed the National Railway to accelerate catenary installation along key corridors like Paris to Lyon and Paris to Marseille, replacing diesel engines with electricity generated by domestic power plants. Across the border, West Germany reacted with equal urgency. In 1975, the parliament passed the Oil Crisis Law, granting the state broad power over energy infrastructure. The government initiated a dedicated rail program that provided direct subsidies and low-interest loans to methodically wire the remaining main lines. By the early 1990s, more than 60% of German train kilometers were electric. For Switzerland, the drive for independence was even older. Lacking domestic fossil fuels, Swiss planners had already wired most of their network by the mid-1930s to tap into abundant alpine hydropower, turning transport self-sufficiency into a national defense policy. Over the decades, these early defense strategies transitioned into modern environmental mandates. Supranational targets from the European Union, including the Fit for 55 climate package, kept the momentum going. Because these railways were state-backed, governments could prioritize energy security and carbon reduction over near-term balance sheets. They treated overhead wires as vital public works, turning a technical alternative into a continental habit. Every time a passenger train pulls out of a station, it fights a battle against time and inertia. For a network built around moving people, the primary operational challenge centers on the constant cycle of deceleration and acceleration, rather than sustained cruising. A regional train that stops every 10 or 15 miles to exchange commuters loses precious minutes at every platform. Under diesel power, heavy locomotives labor to drag passenger coaches back up to speed, wasting energy and time in the slow transition. Electric traction fundamentally changes this dynamic. By drawing energy directly from an overhead catenary, electric trains can pull massive surges of current during acceleration, jumping forward almost instantly. They reach top operating speeds in a fraction of the time and distance required by diesel. For commuter and regional services with frequent stops, this rapid acceleration shaves valuable minutes off daily timetables, allowing operators to run more trains per hour on the same congested corridors. This physical advantage cleared the path for high-speed travel. When France launched the TGV in September 1981, Running at speeds of 270 kilometers per hour between Paris and Lyon, it proved that high speed and overhead wires were inextricably linked. This iconic train was built specifically to compete directly with commercial aviation on long-distance routes. Delivering that level of performance required a continuous supply of 25 kilovolt alternating current, drawing massive amounts of power that no onboard diesel engine could ever carry. Since the late 2000s, this high-speed passenger model has expanded across the continent. Europe's dedicated high-speed lines grew to over 8,500 kilometers, representing an expansion of more than 80% since 2008. From Spain's AVE network to Italy's domestic high-speed links, speed became the central argument for rail modernization. In a passenger-centered system, overhead wires became the essential physical foundation of fast, competitive transit that modern networks require. In the early decades of the 20th century, neither Europe nor North America had a preordained destiny. Parallel futures seemed entirely possible. Switzerland, facing steep alpine grades and lacking domestic coal, electrified its vital Gotthard line with a 15 kilovolt alternating current system by 1924, powering it with state-owned hydroelectric plants. Around the exact same time, the Pennsylvania Railroad mapped out a massive catenary network along the busiest passenger and freight corridors of the American East Coast. By 1935, the Pennsylvania Railroad completed an 11 kilovolt overhead system stretching from New York to Washington, costing $260 million. It was one of the most advanced electrified main lines in the world. But these early parallels dissolved as institutional frameworks hardened. The separation of passenger and freight operations occurred permanently in 1971 with the creation of Amtrak, which took over struggling inner-city passenger services but left the physical tracks in the hands of private freight companies. 9 years later, the Staggers Rail Act of 1980 deregulated freight rates and service contracts. This legislation saved the bankrupt American rail industry by allowing freight carriers to focus strictly on heavy-haul, long-distance efficiency, solidifying their reliance on flexible, low-overhead diesel fleets. These historic forks in the road created a powerful path dependency. The decisions made in the mid-20th century locked both networks into their respective configurations. Today, the physical presence of overhead wires in Europe and their near-total absence in America are not temporary technological gaps, but the permanent architectural footprints of two entirely different historical designs. An overhead catenary line requires continuous active management. It is a sensitive system under constant mechanical stress. The contact wire must be kept under thousands of pounds of tension to prevent sagging, requiring heavy counterweights or automated tensioning devices. Every time a train's pantograph sweeps underneath at high speeds, friction wears down the copper. This demands continuous monitoring, regular wire replacement, and specialized maintenance fleets. Beyond physical wear, the environment presents constant hazards. Freezing rain coats the wires in ice, causing severe electrical arcing, while high winds can snap the overhead supports. Nearby trees must be aggressively pruned to prevent branches from touching live wires carrying up to 25,000 volts. Managing these operational logistics is a natural part of daily business in Europe. On a compact corridor hosting dozens of passenger trains every hour, the cost of specialized maintenance crews, substation inspections, and vegetation management is easily amortized by high traffic volume. The system's high frequency justifies its continuous preservation. But on a remote American mainline, where only a handful of massive freight trains pass each day, this endless upkeep is a major operational liability. A single downed wire in a remote mountain pass can halt a transcontinental supply chain for hours. Keeping maintenance teams and specialized equipment stationed along thousands of miles of empty prairie to service empty space is a financial impossibility. For private railroads, the simplicity of self-contained diesel power remains the ultimate defense against these daily overhead complications. The century-long dominance of the self-contained diesel locomotive is no longer entirely unchallenged. Across the United States, rising climate mandates, corporate green targets, and state-level environmental regulations are forcing private Class 1 railroads to rethink their propulsion strategies. Yet the physical and financial barriers to building a nationwide 140,000-mile overhead catenary network remain absolute. The solution in the American sector is not a sudden, massive shift to European-style wires, but a pragmatic, step-by-step shift built around alternative fuels, battery technology, and highly localized infrastructure. High-capacity battery electric locomotive trials are leading this shift. During 2025 and 2026, the Wabtec FLX Drive program entered active field testing on mainline routes. These retrofitted locomotives carry massive lithium-ion battery packs that work alongside traditional diesel engines or operate independently in zero-emission zones, such as urban rail yards and terminal areas. By capturing energy through regenerative braking on downhills and during deceleration, these units can cut carbon emissions by 20 to 30% on test runs. Because the FLX Drive architecture is modular, it allows railroads to upgrade propulsion systems over time, avoiding the immediate risk of obsolete fleet investments. Where batteries face range limitations on long, heavy haul routes, hydrogen fuel cells offer a secondary pathway. On the Gulf Coast corridor, CPKC is piloting a dedicated hydrogen-powered locomotive. This unit employs a 900-kilowatt fuel cell power pack to generate electricity on board, feeding traditional traction motors while storing pressurized hydrogen in specialized tanks. Coordinated with the Federal Rail Decarbonization Pilot, this program tests how hydrogen performs under heavy freight loads and addresses the practical realities of retrofitting existing terminals for high-pressure refueling, aiming to lower particulate emissions by 30%. Rather than waiting for these technologies to mature fully, major carriers are deploying immediate, lower-risk, hybrid systems. Norfolk Southern and Union Pacific have budgeted for 150 to 200 hybrid diesel battery units to enter service by 2027. By installing 2 megawatt-hour battery packs under the frames of standard locomotives, operators can capture braking energy and use it to boost acceleration, dropping fuel consumption by 10% on regional routes. Where physical wires are considered, railroads are focusing on targeted corridors instead of total network electrification. Under a joint initiative by the Federal Railroad Administration and private carriers, selective electrification pilots focus on critical bottleneck segments. Plans cover 3 zones: 120 route miles of catenary in the Pacific Northwest between Seattle and Portland, an 80-mile system in the Mid-Atlantic between Baltimore and Philadelphia, and localized overhead wires on steep mountain grades along the Gulf Coast. These systems allow dual-mode locomotives to run under external power where emissions are most strictly regulated, then switch to onboard diesel or batteries elsewhere. The future of American rail is not a single, clean-cut choice between diesel and overhead wires. It is a highly complex, mixed technology environment where varied regions and routes deploy specific tools. By matching specific routes with specific technologies, whether battery, hydrogen, or selective catenary, U.S. railroads are attempting to clean up their networks while retaining the private, flexible, long-haul performance that made their freight system a global powerhouse. Today, our rails remain mirrors of the societies that built them. One is optimized for moving people, the other for moving tonnage. As both networks face the urgent pressure to decarbonize, their futures will look as different as their pasts. There is no single superior system, only the unique trade-offs of geography, economy, and national priorities. Which approach makes more sense for the future? Share your thoughts in the comments.